going to listen to a second talk today by Lovitz, and he's going to talk about Nullstellensatz-inspired algorithms for certifying entanglement of subspaces.
Thanks, Yaron. Thanks so much for putting this conference together and having me. Yeah, so I'm going to be speaking about joint work with Nathaniel Johnston and Aravindan Vijayaraghavan on Nullstellensatz-inspired algorithms for certifying entanglement of subspaces. So the basic question that I'm going to be talking about today is you have some subset of Cn that contains 0 and a linear subspace, and you want to describe the intersection or how these relate to one another. So there are a few different questions I'm going to consider today. One is to certify that the intersection of u and x is just a 0 vector. So x will have the 0 vector in it. So the intersection of u and x will always have the 0 vector, and certifying that this is the only element. Second is, well, if this is the case, then computing the distance between u and x, like the distance between any two unit elements. And third is, well, maybe they do intersect, and in that case, finding elements of the intersection and even proving that you've found all of the elements of the intersection. So I'm going to start by going over applications of these three questions for certain examples, and then we'll get into algorithms. So let's start.
One more time.
Go ahead. Yeah.
So they're just touching. U and x are just touching.
They're just touching, or they're not? We don't know yet.
So it's distinguishing, like to know whether it's only 0, something else, or completely disjoint.
Yeah. Well, yeah. We'll get into details. Yeah. So let's look at this example of the set of rank 1 elements of Cn tensor Cn. That'll be x. And in quantum, we call a subspace of Cn tensor Cn entangled if its intersection with the rank 1s is just the 0 vector. And every non-zero element is entangled. So there are a few applications of this in quantum information. First in entanglement witnesses. So a projection matrix on Cn tensor Cn is called an entanglement witness if for every separable input, it has some chance of not outputting the kind of, if you think of this as a measurement like m and I minus m, you have some chance of projecting onto I minus m for every separable state.
So wait, so definition is the same. Every non-zero element has rank at least 2. In the definition.
Yes, exactly.
Yeah.
And this turns out to be equivalent to looking at the image of your projection and saying that it's entangled. So this is like an entanglement witness is a measurement on states that tells that can witness entanglement. Like if you get if you get this outcome of the measurement every single time, it's pretty likely that your input state is entangled, because any separable state will have some chance that you don't get this outcome. The second application is in detecting entanglement of a state. So you have a density operator. Telling whether it's entangled or not is a difficult problem. But one way to tell is by looking at the image. And if the image is entangled, then the state turns out is entangled. This is called the range criterion to detect entanglement. A third application is in quantum error correction. So you can use these entangled subspaces. If U is an entangled subspace, you can use it to make a quantum error correcting code. Okay, these are, I realize this is all very vague, but it's just a motivation for this mathematical question of you start with a subspace, you want to know if it's entangled or not. Okay, let's look at the computing the distance between two. So
one entangled, what is the one referring to?
One refers to, like, you can generalize it to R entangled, which is having every non-zero element has a rank at least R. At least R plus 4. Okay, any questions? Okay. Second is computing the distance. So let's take x1 again. And I'm going to so we say that a subspace is epsilon entangled if, and I'm not going to define the distance yet, but if kind of abstractly the distance between u and x1 is at least epsilon. And this allows you to kind of have a more fine-grained, there's actually way more applications of this more refined question. For example, you can kind of study how good your entangled witness is. You can compute the geometric measure of entanglement or injective tensor norm. And if you're not happy with these, you can look at this paper of Aaron Harrow and Ashley Montanaro, where they have 21 more applications, including determining acceptance probabilities of QMA2 protocols and determining ground state energies of mean field Hamiltonians. They all kind of, there's a lot of questions that just boil down to this basic primitive. Okay, so let's look at the computing the geometric measure of entanglement, kind of more in depth. So here, actually, your subspace is just a single element, a single tensor, the span of a single tensor. And the geometric measure of entanglement, also known as the injective tensor norm, is exactly the distance from T to the set of product tensors. So this is an example where you're computing the distance between a linear subspace and a set. All right. Third is to find elements of the intersection of a subspace with a variety, and this is going to have applications more in like statistical machine learning. So not really quantum as far as I know. So the application is in tensor decompositions. So this tensor decomposition is an expression of a tensor as a sum of rank 1 tensors, or product tensors. And then the rank of a tensor is the minimum R for which there exists a decomposition into R product tensors. And you know, a nice thing about tensor decompositions is that they're often unique. So there's only one rank decomposition. And what I mean by this is that I say that this is the unique rank decomposition if for any other rank decomposition, the product tensors appearing in the sum are just the same ones that appeared in the original one. Up to, you can like permute the terms in the sum, but up to that, yeah, you have this nice property of uniqueness. So as a picture, you start with a rank decomposition of a tensor, so it's rank 5. We say that this is the unique rank decomposition of the tensor if for any other rank decomposition, maybe you have to permute the terms, but you get that stuff. I'm very, very proud of this. Okay. So here's the application of, you know, you have a subspace and you want to compute elements of the intersection of the subspace with the variety, with the rank 1 matrices. Here's the application of tensor decompositions. If we look, so we have an n by n by m tensor. If we look at the, you know, T as a map from Cn to Cn tensor Cn, and we look at its image, okay, so we're looking at kind of a flattening here. And if it has a basis, if its image has a basis of the form of product tensors, then this gives you a decomposition of the tensor. This immediately gives rise to a decomposition of the tensor where the zi's are uniquely defined as the, you know, you take a dual basis and you apply T to the dual basis. Is this okay? Okay. So algorithms for finding elements, so you have a subspace here, and you want to find elements of its, you want to find rank 1 elements in subspace. So algorithms for finding elements of the intersection of a subspace with x1 leads to tensor decomposition algorithms. And furthermore, uniqueness kind of translates over too. Like if this product tensor is the form of the basis are the only elements of the of this intersection, then this is the unique rank decomposition of T.
Where T with respect to U?
Sorry, T, U should be T of Cn, the image of,
Okay.
yeah.
The only elements of the intersection. But meaning like a basis.
So it turns out I'm kind of restricting that T of Cn has a basis of this form.
Yeah.
And I'm restricting that these are the only elements of the T of Cn that are product.
But it's a specific case, right? You could have cases where, in order to span it, in order to be able to express it,
Absolutely.
You're not inside.
Yeah, so this is a very special case that T of Cn has a basis of this form. Yeah. So here's an application of uniqueness of tensor decompositions.
And that was good.
Yeah.
Sorry.
Go
Once
ahead.
again. Let's see. I'm confused because T is, you know. No. Okay. We got it. Sorry.
All right. So here's an application of finding tensor decompositions and proving that they're unique in statistical machine learning. So let's let A, B, C, and L be finite random variables, such that A, B, and C are conditionally independent depending on the outcome of L. So what this means is that condition on outcome little l for big L, the probability of outcomes A, B, and C factor as the product of probabilities. So this is an assumption. And the setup is that like A, B, and C are random variables you can measure, and you can look at them. And L is like this latent random variable that you can't measure directly, but you want to know information about it. And you have this like underlying assumption that if you don't know anything about it, you don't know anything about it. You can't say anything. But you have this like assumption of conditional independence. And using your observation for A, B, and C, the probability vector of A, B, and C, you want to determine the full joint distribution. So one way to do this is through tensor decompositions. We can write the probability vector of A, B, and C. We can expand it over the outcomes of L. So L exists out there. We don't know what it is, but we know that this expansion exists. And then the assumption of conditional independence exactly corresponds to this conditional probability vector being a product tensor. Okay, so we know this L is out there, we don't know what it is, but we do know that it gives rise to a tensor decomposition of the probability vector of A, B, and C. And if this probability vector has a unique rank decomposition, that means there is a unique latent random variable with the minimum number of outcomes that gives rise to this probability vector of A, B, and C. Okay, and this is kind of, in my impression, okay, you usually want these to actually be like continuous random variables and things get more complicated, but this is the basic idea behind a lot of applications in machine learning of finding and certifying that a tensor decomposition is unique. Okay. Any questions? Okay. All right, so we can't do this. We're gonna have algorithms for all three of these things. That's gonna be the top. And we can't just deal with any set. We're going to take a conic variety, okay, a variety that forms a cone. So like a projective variety, the affine version. I just like thinking about affine space. So this talk is going to basically say that at least 2 out of 3 of these problems are easy, provided that U is generic, chosen at random, and the dimension of U is not too big. Okay, number 2 is not. We're not going the 1 and 3 are not going to be too bad. Okay. All right. So let's talk about varieties. So a subset of Cn, I'm going to let V be Cn, and a subset is a variety if there exist some polynomials for which x is equal to the 0 set, those polynomials, and x is a conic variety if it forms a cone. The question is, you have as input, you have like these polynomials, and you have this subspace presented to you as a basis, and you want to describe the intersection. So, for example, we can take our set of rank 1 vectors or matrices, and this forms a variety. So, for example, if n equals 2, then this is the same thing as looking at rank at most 1 matrices. And this is exactly the set of matrices where the determinant is 0. So the determinant is a polynomial in the matrix entries. So this is the 0 set of this determinant. Similarly, for n by n, in the n by n case, it has rank at most 1 if and only if the determinant of every 2 by 2 submatrix is 0. So x1 is cut out. How many polynomials do you need? Well, you need to pick a 2 by 2 submatrix. So you need to pick 2 rows and 2 columns. So there's n choose 2 times n choose 2. Okay, and they all have degree 2. So other examples of varieties that pop up in quantum information anyway are the Schmidt rank at most R vectors, product tensors over more factors, biseparable tensors, tensors that have some flattening of rank 1 across one of the 2 to the m different cuts, or 2 to the m minus 1, and slice rank 1 tensors, which is some 1 versus all flattening. Is rank 1, and then matrix product states with open boundary conditions. This is the ones that have rank at most R with respect to one of the, you like cut it in half in some way, left and right. Okay. So this, studying varieties in general let you have all these kind of give you a host of examples.
What did you say the matrix product states?
Yes. So this is, I should have just written it down. Or not written it down. So it's like you take, it's the elements of
you
Cn
restrict the
tensor.
font dimension or something?
bond dimension almost R. Okay. Okay. All right, so in this talk, I will be proposing algorithms for all three of these questions when X is a conic variety. All right, so the algorithm is going to be, the input is a set of polynomials that cut out the variety and some basis for U. And you want to help with some proof that the intersection of U and X is 0. All right, so how hard is this problem? So in this example, actually it's NP hard. And the best known algorithm takes time exponential in root n. And it also requires some promise that either U is like epsilon entangled or it's actually contains an entangled, a rank 1. Basically, what this algorithm is doing is like searching over rank 1s and trying to find one that's epsilon close to your subspace. So what we have is we have a polynomial time algorithm, or an algorithm that is guaranteed to run in polynomial time, provided that the dimension of U is small enough and U is generic, so randomly chosen. So for example,
when you say certified intersection is trivial, do you mean that you're already assuming that it is trivial when you find?
No, I mean,
or decide is it a decision problem?
It's a decision problem.
Okay.
So we're going to get that. We're going to get the in polynomial time we either output fail or we do certify. Yeah.
And what is the if it's generic?
Generic means that you pick the subspace, you pick a basis at random, and then with probability 1, we're gonna certify that it's gonna be entangled with probability 1, and we can prove that it is. Our algorithm will show that it is, and so the algorithm is a Nullstellensatz certificate. But what's new is so that's something that's known in algebraic geometry. But what's new is like this kind of polynomial time guarantee for generic instances. So for example, if you take a generic subspace of Cn tensor Cn, and it has dimensions small enough, it will trivially intersect x1, it'll be entangled, and our algorithm will certify this in polynomial time. So the maximum dimension of a subspace that trivially intersects x1 is n-1 squared. So we have, you lose a factor of 4, and you have this genericity assumption. So what do I mean by this genericity assumption? I mean that if you pick a basis for U, independently at random according to some measure, for example, uniform spherical measure, then with probability 1, all these things happen. Or you can think about algebraic definition that there's a Zariski open dense subset of the R tuples of Cn tensor Cn for which this thing happens.
Big R being the dimension? Or
Yes, thanks. Yeah, I did not put this. Yeah, big R is the dimension. Thanks. Yeah. You okay?
Or a cat on the dimension.
Yeah. Yeah. Okay. We also have a result. This is kind of bleeding into the finding elements, but let me just kind of mention what are the finding elements of the intersection the statement's going to look like. For a generic subspace of the same dimension containing a generic element of x1, we have an algorithm to recover this element. So this is the only element, and the other going to recover that. Yeah. So what I mean by this is like, if someone that I trust, but someone else picks an element of a rank 1 element at random, and r-1 random elements of Cn tensor Cn, and then hands me some other basis for the subspace that they span, then I can this kind of planted element of x1. Or algebraic definition is there's a Zariski open dense subset of, you take x1 and then Cartesian product that with a bunch of, okay, so like v1 will be in x1 and then v2 for vr will be in here. Is this okay? This good? Okay. Okay. All right. So this is the only kind of numerical table that I'll show, but just make the point that these things are not only polynomial time, but they really are. This algorithm really is efficient in practice. So we can certify for 10 by 10 matrices, we can certify entanglement in subspace up to dimension 63 in 5 seconds.
What are you writing?
MATLAB. Yeah. So we have a more general statement. So to show you x1, we can do the same thing for arbitrary varieties. Okay. So take any conic variety that's cut out. So it's cut out by homogeneous degree D polynomials. Okay. And without loss of general, like if it's cut out by degree D polynomials, then it's some fraction of n plus d minus 1 choose d many polynomials, because that's the space of homogeneous degree D polynomials is of this dimension. Okay. So it's completely general conic variety. Then for a generic linear subspace of this dimension, it will trivially intersect your variety, and there's an algorithm to prove this sometime. That's the order D. What do I have to say? For example, if d equals 1, then x is cut out by linear forms. It's just a linear subspace. And the theorem, kind of reduces to something trivial. So if you take a generic subspace of dimension no greater than the codimension of your linear subspace x, then it trivially intersects x, and this can be verified in poly at time. Okay, because here d is 1, so this is just kind of n delta, which is p. Keep going. So for this, the scaling is not bad. It takes the variety is presented to you as polynomials. So it takes n plus d minus 1 choose d time just to read off those polynomials. Okay, so this kind of gives us a kind of curious upper bound on the dimension of a variety in terms of the number of polynomials that cut it out. So there's this fact that if there exists a subspace of a certain dimension that trivially intersects x, then what's called the cruel dimension of the variety is at most n minus the dimension of the subspace. And then if you maximize over this dimension, you actually get equality here. So this gives you an upper bound on the dimension of a variety in terms of the number of linearly independent polynomials that cut it out. So intuitively, this corollary is kind of intuitive. Like if you have more polynomials that you needed to cut out your variety, in other words, delta is big, then the dimension is going to be smaller because you get a smaller set when you take the zero set of more polynomials. More polynomials have to be 0. Okay, so this is intuitive, but I haven't seen something like this, or even any relation. Yeah, I'd be interested to know if there's any results like this out there. Okay, so delta is not like a God-given thing. The same variety can be cut out by a different number of linearly independent homogeneous degree D polynomials, and if you maximize that number, you get the Hilbert function of x.
Maximize the number of polynomials that you need to cut.
Yes.
But so that they are still linearly independent.
Yes, exactly.
Okay.
You're taking, you have a set of polynomials that cut out your variety, then you're taking the radical, you get more polynomials. Yeah. So let me kind of blow this up. This same result. I just want to, what is this? What's going on? Is there a geometric reason for this? I don't know. Okay. Okay. All right, so for example, if delta is constant, you'd have some family of varieties, then you can certify entanglement in subspaces of dimension up to order n, the largest possible. So this ends up being the case for many varieties of interest. So for example, for x1, it's big N is n squared, little n squared. Number of polynomials is n choose 2 squared. The degree is 2, and delta by definition is this fraction. So this is omega of 1. So we get the result I already mentioned, which is 1/4 n minus 1 squared. This is order n squared. Other examples. So we get similar kind of nice scalings for all of these examples. We can certify generic subspaces of that a generic subspace does not intersect the rank at most R vectors of dimension, the subspace's dimension omega n squared. And for product tensors in M systems, we can go up to a constant multiple of the maximum dimension. Similarly for biseparable and slice rank ones, and for matrix product states too. Yeah, what is the Hilbert function of the matrix product states? I don't know. But for the other ones, we kind of know the Hilbert function. This one, I just use like a trivial bound on it, but I actually don't know how many linearly independent degree R+1 polynomials do you need to cut out the matrix product states? I don't know. Okay, and this is all in poly time and system size. What is the algorithm? Okay, so it's just a Nullstellensatz certificate. Really, it's the guarantee that is new. So the input is a bunch of polynomials that cut out the variety and some basis for u, and we want to prove that u trivially intersects x. So to describe it, I'm going to need a few notions. So let's let SD of v be the symmetric space, the set of tensors that are invariant under permuting the systems. And so for example, you take any vector v tensor d is a symmetric tensor, as well as v1 tensor v2 plus v2 tensor v1, because if you swap the two systems, you're just changing the order of the sum. But if you take v1 tensor v2 minus v2 tensor v1, this is not symmetric, because if you swap, you pick up a minus sign. So I'm going to use inner product. I'm not sure if these results require an inner product or not. I haven't worked through them, but we're going to use it. So we're going to take let p, this v thing is meant to be like the opposite of the wedge, so it's like a symmetric. The opposite of wedge, the opposite of antisymmetric is symmetric. And this is I'm going to find this to be the orthogonal projection onto this subspace.
It's actually used for dual sometimes.
True. All right, so note that a basis, you can take a basis for the symmetric space, given as follows. Well, to get a spanning set, we can just take, the set of, the computational basis or the standard basis and take their projection, but then some of those end up being equal, namely the ones that have the same tuple of i's in there. So a basis for this space is you project onto the symmetric space of these standard basis vectors, but they need to be non-decreasing, so that you're kind of throwing away the ones that give you the same projection. Okay? Okay. Okay, this is the most important slide of my talk. We can use this equivalence between conic varieties and things. I like working with projections and linear maps. So this is, So this is, okay. X is a conic variety if and only if there exists this projection matrix that is symmetric. Its image is contained in the symmetric space, and it picks out the elements of X in this way. The elements of X are exactly the elements of V, for which V tensor D is in the image of psi. So this is like the most important bullet point in my talk is this. So we're going to kind of now, okay, how do you get it? So if X is cut out by these homogeneous degree D polynomials, F1 through Fp, we can view these as linear forms. We can view these as elements of SD V star. And then we take psi to be the projection onto the intersection of the kernels of all these Fs. Then an element V is an X if and only if these polynomials applied to V is 0. Viewing these polynomials as linear forms, this is equivalent to these linear forms applied to V tensor D being 0. But by definition, how we've defined psi, this is exactly V tensor D being the image of psi.
So these kernels are not linear, right?
These are linear forms on SD of V.
Ah, the F1.
Yes. Okay.
Can we
Yeah, I see.
give more details on that?
No, I see. Okay.
You okay?
Okay. So the D is the D. That's probably what he said, but I didn't listen. The D is the same D that is the degree of the nominal constant.
Yeah. So these are homogeneous polynomials of degree D.
Yeah. That's why we can look at it as
Okay. For example, if X is the set of rank 1 elements of C at tensor Cn, it's cut out by degree 2 polynomials. And you can take psi to be the projection onto S2 of Cn, tensor S2 of Cn, where here I'm looking at like, so this is a projection onto Cn, tensor Cn, tensor Cn, tensor Cn, and I'm projecting onto like, so if we take 2 copies, I'm taking like an S2 to Cn, tensor S2 to Cn, and this is like this guy and this guy. So this is psi, the projection onto this. So it's clear if you take an element of x1 and tensor product of it with itself twice, it's going to live in here. This is going to be a v, and this is going to be a v. This is going to be a w, and this is going to be a w. And then, you have to verify for yourself that those are the only elements of this form. One thing I have to say is like getting from, translating between the polynomials and the projection is polynomial time. So just from now on, I'm going to be just regarding X as being presented by this projection. So you're really, you're presented, you don't need to be presented with the generators for the ideal of X. You just need to be presented by some polynomials that cut out X, and that you translate that into some projection. Okay, here's the algorithm. You have as input X presented to you as the, in terms of this projection, and you have input some subspace, some basis. What you do is you check that if the image intersected with the symmetric subspace of U tensor D is 0. And if it is, then you output that yes, these trivially intersect. There's nothing inside. Otherwise, you say, I don't know. So for correctness, we need to prove that, if this intersection really is 0, then it really does hold that the intersection of U and X is 0. So this is clear, because if you have an element of the intersection of U and X, then U tensor D is in SD of U by definition of SD of U, and then U tensor D is also in the image of psi XD because U is an X.
Is the length of inputs when I get that operator, and had I gotten the polynomials, is it comparable? Is it the same? I haven't thought of it, just
the length
question. Yeah, because you changed with the algorithm, you changed the question in terms of what the input is. I'm trying to understand if you did.
So yeah, my point is that you can translate between the two
right.
In polynomial time. So you just, given the polynomials, you can construct this projection.
But
you have this projection,
the number of the length of it is also.
The
well, if you can translate it, must be
the length, like the rank of the.
No, just.
Oh, what the presentation is. Okay.
Yes.
Well, this is a projection on the symmetric space, so it's still like maybe I lost some factor, but it's like the polynomials are like n plus d minus 1 choose d size, and this is a projection onto a subspace of n plus d minus 1 choose d dimensional space. So we're thinking of a matrix that's like k by k instead of polynomials that are each k dimensional. Okay. Okay. So is this clear, this slide?
So, but why does it not always work? Why is there a second phase actually? Like, why is it not known?
Because yeah, so if you get an element of this, it might not be the case that what you really need is you need a product vector in here. So the theorem, it comes from proving, and I'd say a little bit about what the theorem, how we get it is that you really want to prove that for a generic subspace of dimension not too big, the image and the symmetric space don't intersect. Like this, the algorithm you have outputs the right answer. Okay. So the idea, I mean, it's just like now kind of a complicated linear algebra question. You're given some subspace. We even forget that it comes from a variety, just some subspace of symmetric space. We want to show that a generic subspace of the form SDU, for dimension U not too large, satisfies this. Yeah, I'm just taking the variety out of the picture. This is how this is proven. Okay, we're just starting with a subspace. You want to find like a complement of the form SDU. So, I mean, any two subspaces that have dimensions summing up to something bigger than the ambient dimension, the n plus d minus 1 choose d, if they sum up to something bigger than the ambient dimension, of course they're going to intersect. But you could hope that you could just, take R that like maximizes, is like, for which this sum is maximal and still satisfies this inequality. Does that make sense? Okay. But this is not true. So you can't, it's kind of, yeah, this is a non-trivial question. So you take n equal 3, d equal 2, and take w to be, so you're looking at S2 of C3, and take w to be S2 of some C2 inside of C3. So some pattern with zeros to view it as an element of S2 of C3. And for any subspace of C3 of dimension 2, it turns out that that's kind of what maximizes this. The intersection of W with S2 of U, it contains S2 of the intersection of C2 and U. But since we're working in C3, we have two subspaces of dimension 2, they must, C2 and U must intersect. Okay, so this is like all I'm going to say about the proof. It's just this kind of linear algebra question, finding a complement of a symmetric subspace of a large dimension that's of this particular form. Okay, so for a complete hierarchy, we can just tensor our psi with identity. So for each c greater than or equal to d, we take psi tensor identity. And then the algorithm goes like, if you check all the c's and they're all 0, if there's some c for which the intersection is 0, then you output yes, but they really trivially intersect. There's nothing in the intersection. And otherwise, really, you could say no. This is by going up the line here. So correctness, one direction is just the same thing we saw before. Like if you have u in u intersects c, then u tensor c is both in the image of psi x c, and it's in the symmetric space of. And then the other direction is Hilbert's Nullstellensatz, and then it's agreed on. But this whole thing is just a complicated way of talking about Hilbert's Nullstellensatz. Okay. But I think it's, I don't know. I mean, I think it's useful for what we'll do next. I think. We move on. So I'm going to move on to determining the distance between u and x. So the input is polynomials cutting out x, a basis for u. And you want to output some lower bound on the distance, and we're actually going to get a hierarchy of eigenvalue computations that converge to the distance. So yeah, that's what I said. So to turn this into a kind of robust version, so this is like, I think of this as like a robust version of the Nullstellensatz certificate, basically, what we're doing. We're making this Nullstellensatz certificate algorithm robust. So the first way to do this is, the first ingredient is to observe that we can phrase this algebraic condition as a condition on the maximum eigenvalue of a certain matrix. So this matrix here is a product of 3 projections. Okay, you project onto the subspace U, tensor identity on the rest. You take psi, which is itself a projection, and you take the projection onto the whole symmetric space. So why is this true? Well, the maximum eigenvalue of the product of projections is less than 1 if and only if there's nothing in the intersection of the images of those projections. The maximum eigenvalue of a product of projections is less than 1 if and only if there's nothing in the intersection of the images of those projections. So this is equivalent to the image of this P intersecting with the image of psi, intersecting with the image of this guy, which is U tensor B tensor C minus 1 being 0, which is in turn equivalent to, basically you put together the symmetric space of V with U tensor V, you end up with the symmetric space of U. Okay, I'm going to put 2 more guys over here. Okay, this doesn't matter. Again, you have product of projections, the same proof goes through, but this is nice now because now we have a Hermitian matrix here. I've just turned this into a Hermitian matrix, and computing maximum eigenvalue of Hermitian matrix is nice and fun. You know how to do it. So I'm going to let this be nu C. Okay. All right, so we have our hierarchy now becomes, if nu C is less than 1 for some C, we output yes. All right, so let's define the distance before we go any further. So the distance between U and X is going to be defined to be the minimum 1 norm squared of the between, you take the difference between an element of X, XX star and UU star. This is a Hausdorff distance between the 2 sets, and I have 1/4 because it'll make everything work out nicer. So it turns out this is 1 minus the maximum overlap squared between 2 elements. And you can also simplify this down to just taking 1 minus the maximum overlap of an element of X with the projection onto U. Okay, so here's the theorem, is that actually, we know that if nu C is equal to 1 for all C, if and only if the distance is 0, then you might hope that if nu C is smaller than 1, then we can get some control of what the distance is. And so we get this exactly. The distance is exactly 1 minus the limit of these nu C's. So in particular, we have this hierarchy. The distance is, first of all, it's greater than or equal to 1 minus nu C for any C. And if you take the limit, as C goes to infinity, you get the true distance. So we get kind of a hierarchy of lower bounds on the distance.
I have a question.
Yeah.
So, I mean, the distant point may be not unique, right?
Yes.
So where do you see this non-uniqueness over in your...
So, I mean, it's kind of similar to how in Hilbert's Nullstellensatz, you have like, if you run the Nullstellensatz and check it for every, up to like t minus 1 to the n, and in every case, you have something in the intersection of these 2 subspaces, like, then you know that there's some element of the intersection of the 2 of U and X, but you don't know what it is. You just have this guarantee. Similarly here, we're like kind of not looking at the elements. So there, maybe this is, like there are many algorithms that do compute upper bounds on the distance by just finding 2 elements, finding an element of U and finding an element of X, computing the distance between those 2. And that gives you an upper bound on the distance. But I think what's a little bit different about our algorithm, we have a hierarchy of lower bounds on the distance. So we can't look at elements of X and U. We really have to kind of look in the dual picture or something. Saw that already? I'm going to skip the proof. Or should I do proof? Sorry. Maybe I show this one, this factor. So let's show that these are actually, let's show that this inequality holds, which is exactly what I said. Each one lower bounds the distance. So first of all, note that the image of the symmetric projection composed with psi xc, it contains the span of V tensor C, where V is an X, right? So if you're in the image, you're able to form everything in this form is in the image, and if you tensor this with more V's, you're still in the image. So, maybe I write psi xc is very simple. Xc, if that's the way I'm doing it, is equal to, this is just psi xd tensor identity. Identity on V, tensor C minus D times. So when you're computing the maximum eigenvalue of a Hermitian matrix, you can just maximize over the inner product with unit vectors. So in particular, if I choose a particular unit vector, then the maximum eigenvalue will be greater than the inner product of that unit vector with the rest. So this is kind of, I think they look identical. The nu and the v look identical.
Literally.
Yeah, they look identical. Maybe I messed up.
They do.
It's the same. Which is u? What's u?
New.
I might if I knew the maximum eigenvalue. Yeah. Okay. So I'm going to pick an element of pick a v in x and take 8 tensor c times. Okay. The new c is at least as big as this inner product. But now v tensor c goes right through this projection and psi because it's contained in the span. It's contained in the image. So now you have this inner product, but now v is a unit vector. It just hits the identities and goes away, and you get exactly the inner product of v with the projection onto u. So if you maximize over the v's in x, you get that nu c is greater than or equal to the maximum of this inner product, which is exactly 1 minus the distance. That's how we define the distance. Okay, so we know that we do get lower bounds on the distance. And then, you prove that they actually converge to the true distance as you go to infinity. And I will skip this. Yeah. So you set up an SDP. The proof uses basically like symmetric extension. So there's this result in quantum that if you take a mixed state, it's separable if and only if it has what are called symmetric extensions for all orders. And we're working in symmetric space. You set up an SDP where this is like optimizing over a state that's symmetric. And then you basically use each of these row C's to each of these row C's will be symmetric extensions of some smaller guy. So that guy must be separable. I call it tau. And so without loss of generality, you can take it to be a unit vector, just like rank 1. And then, so you get your thing. This is very, very vague. But
So you know how far you need to go in your hierarchy to get close?
No. Yeah. I guess we know, you can say the same thing. We have these genericity results. So you can say that if the subspaces do not intersect and the subspace is generic, then without, at the first level, C equals D, you're going to get a non-trivial bound on the distance. Okay, so now I'm going to look at an algorithm to recover elements of the intersection. So the input is again a set of polynomials and a basis for u. And the output is going to be a set of points in the intersection of u and x. And actually, furthermore, we're going to get a proof that these are the only elements. So, okay, we're either going to output fail, or we're going to output this. So recall our result for certifying that a subspace does not contain elements of x1. We can kind of extend this to an algorithm for finding elements of the intersection. And it's going to be motivated by kind of a similar thing to Nullstellensatz certificate. So what we say is for a generic subspace of the same dimension containing some number of planted generic elements of x1, our algorithm will find these elements and prove and certify that these are the only elements of the intersection. What I mean is that someone out there picks S. S can be arbitrary. You should either think of the S as either being 0, so you're certifying at 0, or equal to the full dimension of U, so U has a basis of elements of x1. And so on the left-hand side, we're in the certify entanglement setting, and the right-hand side, we're in the finding tensor decomposition setting. And in the middle, we can do it, but I don't know how useful it is. So some adversary, or I don't know what to call them, some other person picks V1 through Vs in x1 at random and Vs plus 1 through Vr in the whole space at random, takes that subspace that they span, and just gives me some basis of the subspace. Okay, and then we can actually find those elements that are in there. Algebraically, there exists a Zariski open-dense subset of x1 cross S, cross Cn to Cn, cross R minus 1, for which the whole business happens. So for example, So what this gets as a corollary, we get that for a generic tensor in Cn, tensor Cn, tensor Cm, of rank at most 1/4 m minus 1 squared. You take the minimum of that with m. This has a unique rank decomposition, and it's recovered by applying this algorithm I haven't told you about yet to the image of T. So analytically, this means like I pick T, I pick a bunch of rank 1, I pick R rank 1 vectors, where R is the rank that I'm interested in, or rank 1 tensors, and then sum them together, and someone hands me the tensor that they get, that you get, that'll actually have a unique rank decomposition given by this, and then you can recover them. You can recover it. And then similarly, there's an algebraic definition.
It's a new, that's new. It's a new rank.
It's new-ish. It's, yeah, so
Comparable.
so the algorithm is not new that we have in this case. This was like a similar bound was claimed in an earlier paper, but there's an error. It seems to be, they do a similar analysis as we do, but their proof is incorrect, it seems. Yeah, so this is a, yeah, I'll say a little bit more about it. Okay, I don't know. Should I do the proof?
Now it's 11:15.
What time is it?
1 to 12. 1 minute.
1 minute. Okay, okay. Maybe I don't do the proof. Okay, so there's similar notions of decompositions for arbitrary varieties. Like I call them XM decompositions, where VIs are chosen from X. I'm basically just setting up a decomposition problem where I get this equivalence between finding elements of a variety intersected with a subspace. So this is like decompositions where the VIs are chosen from X and the ZIs are chosen from Cn. We have a similar notion of uniqueness and a similar amazing animation. And okay, so we get like the same kind of theorem as before, where now you're picking generic elements from the variety. You can recover them. And no, there's not really an analytic definition of this. How do you pick random elements of a variety? Maybe you can do it, but I don't know how. Yeah, and then probably you can do it if you know a little more measure theory and differential geometry. But I take Zariski open dense subset of doubles. Okay. All right, so for example, you'd have generic tensors of certain x, comma m ranks can be recovered.
Slice root doesn't.
Yeah, we can't do slice. We need your, oh, sorry. Yeah, this is an important, actually. We need two more assumptions. We don't have an arbitrary conic variety. We need to be irreducible. And we need to have no equations in degree d minus 1. So it's cut out in degree d, and has no equations in degree d minus 1. This is what we need for our proof. Okay. I'm out of time. Yeah. Yeah. Thank you.
Generic is used inside somehow. Is that what I saw?
Yeah, generic is used. Yeah.
So that's what you meant by the algorithm was known.
Good. Yeah, this is actually something that I should talk about for related work. No, so these are like the algorithms. As far as I can tell, it's like the same as the one proposed by Delafleur. They just don't have a genericity claim.
Yeah.
Yeah. I mean, they do, but they have. It's the proof is incorrect, as far as I can tell.
Interesting. So, but I've heard a lot about generics, but yeah, of course.
So you have like the Fubi algorithm. I don't know if you've heard of this.
Fubi.
It's like a decomposition algorithm for fourth order symmetric tensors. And that's, yeah, this is where this, our algorithm is based on theirs and just generalizes its arbitrary varieties and fixes the generic claim.
Also say something the other way around, so when it is not unique. The decomposition.
Like proving that it's not unique? Or
yeah, or maybe computing the dimension of the non-uniqueness of the decomposition.
I don't know.
And also in terms of equations. So, I mean, you really deal with equation of certain degree.
Yeah.
So, Can you say something? I mean, if you have any variety and you have just a bunch of equations certain degree, can you say something from the equation of some smaller degree if they are or not, like the first degree where it is generated, or when you may stop with the equations of your variety?
Not that I'm not sure. That's an interesting question. I guess somehow with picking this subspace, picking a generic subspace and looking at its intersection, maybe, if you know the dimension of your variety and you pick a subspace of its codimension, then you find that it trivially intersects using Nullstellensatz certificate. Maybe that, okay, you can add polynomials without reducing the dimension, right? So it doesn't quite work out, but if that wasn't the case, then you could do this kind of,
More questions? Thanks again.